Okay, so let's look at this next example. It's based on the same equation. So let me rewrite the equation down here. And in fact, we're going to use the same form of the equation that we used in the previous example. Hold on, let me choose my ink. Okay, so if you recall, the equation that we used is K1 over K2 is equal to e to the minus EA over R times 1 over T2 minus 1 over T1, all right? Now, in this particular case, they gave you the first temperature and the first rate constant associated with that. So what I'm going to do is call this T1, 600 T1, and K2 would be the 1.6 times 10 to the minus 5. And then the 700, I'm going to call this T2, and I'm going to call this K2, the 6.36 times 10 to the minus 3 seconds to the minus 1. And what this question is asking for is the activation energy. So this is what the question is asking for. So what we have to do is basically algebraically rearrange this equation in order to determine an expression for the activation energy. So what we can do, and this is something you should have met in your previous algebra courses, you can find a natural log of both sides. So ln K1 over K2 would be equal to minus EA over R times 1 over T2 minus 1 over T1. And then to solve for EA will now become equal to minus R ln K 1 over K2 all divided by 1 over T2 minus 1 over T1. So from here, we just have to plug the numbers in. Now, R is going to be equal to 8.31 joules per mole Kelvin times natural log of K1, which is, we designate that to be 1.6 times 10 to the minus 5 seconds to the minus 1, divided by K2, which we designate to be 6.36 times 10 to the minus 3 seconds to the minus 1, and all that would be in parentheses here, all divided by 1 over T2. Actually, I made a mistake here. This should be T1 and this should be T2. So let me make that correction throughout this exercise here. This should be T1 and this should be T2. So that would be 1 over 600 Kelvin minus 1 over 700 Kelvin, all right? And I worked this out earlier, so I won't spend any time doing it now. I'm just going to let you know that the final answer works out to be equal to 2.09 times 10 to the 5 joules per mole Kelvin, or if you prefer, which is most often expressed as 2.09 times 10 to the 2 kilojoules per mole Kelvin. All right. Okay, so that's basically how that particular example is done. All right. Okay, so the next video, I'll basically be finishing up on this chapter. All right. Until next time.